A constant magnitude force is applied to a rope attached to a crate. The crate is on a level surface. For each of the following situations, circle the correct relationship symbol between the two force magnitudes and explain your reasoning. In part A, the crate moves at a constant speed and the rope is horizontal. So we have our crate resting on the surface. The rope is horizontal, so we have the force of the rope on the crate. And we have the force of gravity acting downwards. We have the normal force, which is perpendicular to the surface of contact. The crate is moving, which means we have kinetic friction, and that must be acting to the left, since if you're pulling on the crate with a force acting to the right, the crate would be moving this way, and friction opposes the motion. If the crate is moving at a constant speed, then the acceleration is equal to 0. We have Newton's second law, which says the sum of the forces is equal to the mass times the acceleration. In Model 2, we can break this down into components and say the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. You have two forces acting in the x direction. The net force must be equal to 0 since the acceleration in the x direction is equal to 0, and that means the force of friction must be equal to the force of the rope. The acceleration in the y direction is also equal to 0, and that means that the net force in the y direction is equal to 0, and that means that the normal force is equal to the force of gravity. Here they call it the force of the surface, that is the normal force. That is equal to the force of gravity. If the crate does not move and the rope is horizontal, then what changes in our free body diagram is that the force of friction that we have is now a force of static friction. We still have the normal force, we still have the force of gravity, we still have the force of the rope. If the crate is not moving, the acceleration is still equal to 0, so the normal force is still equal to the force of gravity, and the force of the rope is still equal to the force of static friction. It's just now static friction instead of kinetic friction. In part C, the crate moves at a constant speed. A constant speed means the acceleration is equal to 0. That's true for the x component of the acceleration and the y component of the acceleration. The rope is inclined above the horizontal. So we have our force of gravity acting straight downward, our normal force, which is perpendicular to the surface of contact, and the crate is moving, which means we have the force of kinetic friction, and the rope is inclined above the horizontal. So we have the force of the rope acting like this. We can break that force down into components. Let me draw that over here. So we have an x component, and we have a y component. And if you add those components together, that gives you the total force from the rope. I'm going to draw a new free body diagram with the components for the force. I have gravity acting downwards, I have the normal force acting upwards, I have the force of kinetic friction here, I have the x component from the force of the rope, and I have the y component that's acting upwards. Okay, now the force of gravity is no longer equal to the normal force because the net force in the y direction is still equal to 0. But now I have this component from the force of the rope which is pointing upwards. So from Newton's second law, sum of the forces in the y direction is equal to 0 because the acceleration in the y direction is equal to 0. That means the upward forces are equal to the downward forces, so I have the normal force plus the y component from the force of the rope is equal to the force of gravity. That means the force of gravity is not equal to the normal force because the normal force plus something else is equal to the force of gravity. That means the normal force must be less than the force of gravity because you have to add something else to the normal force in order for it to equal the force of gravity. So the force of gravity is greater than the force of the surface. This should make sense to you because if you have something resting on the surface, if I pull up on this, the normal force is going to decrease until it comes up. off of the surface. So if I had my calculator on a scale, if I pull up on the calculator, the force of the scale, which is measuring the normal force, is going to decrease. Okay, so the normal force is smaller, the force of gravity stays the same. Then we're going to compare the force of the rope and the force of friction. Well, the sum of the forces in the x direction is equal to 0 because the acceleration in the x direction is equal to 0. This means that the leftward forces are equal to the rightward forces. This means that the force of kinetic friction is equal to the force of the rope in the x direction. This means that the force of the rope is greater than the force of friction because the force of the rope in the x direction, that's just part of the total force. So part of this force is equal to the force of kinetic friction, which means the total force must be greater. The magnitude that you have here, the length for the force of the rope is greater than the length that you have for just the x component of the force of the rope. So the force of the rope is greater than the force of friction.